All righty. Well, TNT Forum we're starting out with. We got a good presentation here from Bill talking about balance. So, Bill, if you're ready, take it away.
I'm ready. You ready, Leon?
I'm ready. Go for it.
Okay, I'm going to share screen.
Yep.
Okay, you should all see a screen now. That's the first slide.
Yep.
Okay, so I feel kind of strange about doing this because the talk that's going to follow me is Roy Wellen tonight, and he's one of the people who has written about balance, and a lot of the experiments I've done is actually based upon his work. So it's save all your questions for him. He really knows this stuff. Okay, that's interesting. My slide does not advance.
Oh.
Okay, we didn't test that. Okay,
Oh, there
I
we
see
go.
how, yeah, but not with the arrow keys. Okay, so balun, as you folks probably all know, is a contraction of two words, balance and unbalance. So it says, okay, we'll take something that's balanced and hook it to something that's unbalanced. Well, in our case, it's almost always the opposite. We're taking an unbalanced thing, that's like the output of our transceiver, to a balanced thing, which is an antenna. So it should probably be called unbow, but in historical reasons, we ended up with balun. But there's also things called unins, which is unbalanced, unbalanced. And this term was actually coined during World War II and was not published in anything until after the war was over. But it's basically been assigned to Alfred at Harvard University Radiation Laboratory. And if you ever look up Alfred, he's done a lot of great stuff. Okay, so where are they usually used? Not in antennas. Push-pull amplifiers are balanced inputs and outputs. So how do you take the output of a push-pull and then it to a speaker, which usually has, that transformer may have one side grounded or that. Ethernet cables, those are all balanced lines. Phone lines, the twisted pair, those are all balanced lines. And yes, it's also used to antennas, but there's a major difference. When it was hooked up to other circuits, through cables and like push-pull amplifiers, the source and load impedance are very well known, well-behaved, within tight limits, while with antennas, especially like off-center fed antennas, that impedance can vary all over the place in huge numbers in the complex impedance of that, which is not what was thought about when these people originally came up with balance. So you have to ask a question, what is actually being balanced? What is balanced? What is unbalanced? Well, in our RF world, we talk about voltage and current flows, like 180 degrees out of phase to the antenna of that's balanced. We talk about balanced transmission lines, talk about balanced antennas, but you have to be careful. If you go around reading literature and they talk about balance, you have to read that article carefully to figure out what in fact are they referring to as actually as being balanced and what's their definition. The IEEE has no formal definition of a balun or balanced. So anybody can invent any definition they want. And so just, beware when you read the literature. So what I'm going to kind of talk about is simple things like dipole antennas, which in free space, they're balanced. You look at them, they're symmetric. This is no trees around them, no buildings around them, nothing else nearby. And it's a very nice balanced antenna. Coax cable is not balanced. But so what happens when we connect a coax to a dipole when it's not in free space? I'll show you that in a little while. So first of all, let's talk about these antennas. So a folded dipole is balanced, right? The two sides of the feed come up, circle around in that squash loop, and it's a very nice balanced antenna. A dipole, which is free space, is balanced, but when it gets like a vertical dipole, that ground effect on the one side is really going to impact the lower side of that dipole versus the upper part, or even a horizontal dipole depend upon where buildings are, different structures, or whatever. Well, how about some other antenna types? Off-center fed, that doesn't look symmetrical. It's not balanced. So I say I want something that converts an unbalanced to a balance, and I'm going to feed an off-center dipole. Well, but the off-center dipole isn't balanced. So why am I using a balun to feed it? Well, how about an edge-fed antenna? That's not symmetrical. That's not balanced. In fact, folks that have nice gamma matches on your beams, you took the fed element of a beam, dipole, which looks balanced, and then you immediately made it an unbalanced element by putting a gamma match on it. But, you know, we still talk about using balance for matching to things that aren't balanced. That's not what balance were designed for. So I said I'd tell you what happens with and without a balun to a dipole that's not in free space. There's an article in QST back in 1980 that shows it. So with a balun, you notice it's still not the perfect dipole pattern. It's still off a bit. But without the balun, it doesn't come close to the dipole pattern. Because what's the balun supposed to do? It's trying to get equal and opposite currents on both sides, both arms of that dipole. They're 180 degrees out of phase. Well, that's why we want to feed these things with something that's balanced. We want to get those currents to be the same on both arms of the dipole. So what's the objective? To ensure that both sides of a symmetrical antenna have equal voltage or current 180 degrees out of phase. Turns out, you know, that the saying is the current does the talking, and what we actually want is the current on both sides. Notice that the purpose of a balun is not to eliminate currents on the outside shield of a coax cable, called common mode currents. Turns out if you had equal and opposite currents on those arms, you won't have those common mode currents, but that's not the intent of a balun. A balun's job is to get those currents to be equal and opposite. How to get rid of the currents on the outside shield of a coax is a different issue that we'll get into a little bit later. So many devices sold to hams that are designed to eliminate common mode currents are in fact not baluns. They're labeled baluns in sales literature. We call them baluns. We use that term all over the place for anything that's a device between a coax and antenna. But you have to ask the question, are they really trying to get equal and opposite currents onto the two arms of the antenna? If that's not what they're designed to do, then they are not a balun. So there's three basic types of baluns. So called voltage, current, and the other one combines the two, and so it's both. So what's the purpose of a voltage balun? It's to put equal and opposite, 180 degrees out of phase is what I mean by opposite, voltages at the feed point of the antenna. A current balun is to have equal and 180 degrees out of phase current on both sides of that antenna. And the third is it tries to do it with both the voltage and the current. Now, that terminology, voltage and current balun, as far as I can tell, was invented by your next speaker, Roy. And it really has helped the literature by having that. And now in the technical literature, in the academic literature, they use Roy's terms. So that's what the difference is between a voltage and a current balun. And you've noticed one uses a transformer as we're used to using transformer. The other one uses it in a different way. But if you actually went through what's happening with the currents, you will see that it does what we want it to do. That paper that I referenced at the bottom, I strongly, strongly recommend anybody who's interested in baluns, read that paper. Roy did a fantastic job in it. It not only discusses these different types of baluns, but it also goes into some modeling so that you can actually see what the impact is on this. And I mean, he used easy neck. You can also use four neck too, as Lee talked about it a few weeks ago. but I've used EasyNet to do this, and he gives experiments, he shows what happens. It's a really wonderful, wonderful paper, and you can find it on the web. It's also in the AWL Antenna Compendium, Volume 1. Okay, so now balance can also be combined with impedance changes. So you hear about 4-to-1 balance, 9-to-1, 1-to-1. All that is trying to do two things with this one device. One is to go from unbalanced to balance, and the other one is to do an impedance change to match something better. So for example, if I'm trying to go to ladder line, I may be using a 9-to-1 to get from my 50 ohms of my transceiver to it, but I also want to be balanced on the ladder line. Okay, so here's actually a picture of a physical device of a balun made by North Hills Electronics. We're up in New York. And if you notice it, on the left-hand side of the picture, right over here, you see it's grounded, so that's the unbalanced side. On the right-hand side is the balanced side. You can do balance with or without a center tap of the transformer. Goes from 20 hertz to 10 megahertz. It's wide band, doesn't go as high as 30. And it's not 50 ohms, but that's okay. But these devices as transformers are sold all over the place, used all over the place where people are doing stuff. It just tends to be not what hams are used to thinking of in terms of a balun, but this is what actually a balun is. Okay, transmission line. So let's go into what they are. So ladder line, window line, open line, all those names. Okay, now up here at the top, those are all balance lines. If you look at them, both sides it's the same. Coax is unbalanced. That center conductor and that shield looks very different, right? So let's see why one's balanced and one's not balanced as a line. So the common thing people say about is, well, with ladder line, you don't ground either side. Well, of course you could ground a side, right? But that's its use. And in coax, nothing says that that shield has to go to ground. It can go to whatever you want it to be. We tend to ground them. But these are intrinsically balanced and not balanced, independent of the fact that they are hooked up to the ground. Okay, so what's the actual definition? Like I said, the IEEE doesn't have a definition, but the Penguin Dictionary of Electronics does. Okay, transmission line, okay, got that. Two conductors of the same type, okay, same type. Ladder line, both conductors are exactly the same type. Coax, that shield and the inner conductor are not of the same type. Each which have equal impedances along their lengths, okay, that they don't in coax, and equal impedance to ground and to other circuits. Okay, that's its use. So if I have a coax and say I wrap it around some a ferrite toroid, the shield side still has a direct path to ground and the center conductor doesn't. So they don't have equal impedances to ground. So that coax being wrapped around toroid does not make a balun, doesn't make a balanced transmission line. We call it that, but we should just realize that that's a name we've given it, but it's not go with the definition of what a balanced transmission line is or what a balun is. Okay, how do you actually measure a balun's performance? You don't measure how much current is on the shield of the outside shield of the coax, because that's not its job. So back in 47, this book down here is the report of what was done by Harvard University in RF during World War II. It's a 2-volume set. It's free download off the web. And what they're actually doing is saying, okay, let's take a balance line, because remember, that's what we were trying to do. Take a quarter wave stub and take an RF voltmeter and actually see what we're getting there. And if we're balanced and we're 180 degrees out of phase, we can see that. Well, you don't see that in the Ham literature of how to measure balance performance. You look in the Ham literature and it's about current on the outside shield. Again, that's not the purpose of a balun. Okay, so what's the balance objective? Equal and opposite voltage current are both on output in relationship to ground. Got it. What's a choke's objective? Prevent common mode currents, currents on the outside shield of coax. Those are very different objectives. Okay, I can attain, if I do this one, chances are I've also accomplished the second one. Okay, but in the second one, I could have total mismatch in current on that antenna, have current coming down on the shield, somehow absorb it or otherwise mitigate it so it doesn't pass my device with a choke, and I still have unequal and not 180 degrees out of phase on the antenna. So the currents on the antenna still give me the weird pattern that I showed you earlier. What we want to do is have both of these going on, okay? We tend to use the choke method. So how do you perceive that? Okay, assume you're feeding a symmetrical antenna such as a dipole with a coax, okay? Current goes up the inside conductor of the coax to one arm of the dipole. It goes up the inside of the shield to the other arm. And what it can do, it can also come down that on the outside of the shield. So how do you force all the current or voltage onto the antenna and to make the, you say, okay, if that path coming down the outside of the shield is really high impedance, well, what does current want to do? It wants to take the path of least resistance. It doesn't want to go down the path of high impedance. So what we do is we try to put high impedance on the path of the outside shield. That's a choke. So here I'm just showing what I just said. So we have current on the center conductor. Current on the inside goes up. Parts of it goes out on the arm of the dipole. The other side comes down the outside of the shield. Okay. Here's the model. In that paper that Roy did, he goes into this model quite extensively. So easy to do in EasyNet, right? You got this wire coming down here. Let me tell you, you put a signal generator there at some frequency. If this is a quarter wavelength long and this is not, guess what the current wants to go? It wants to go down this resonant path. I've done that model and it's just like, okay, this is the path of least resistance for me, not this. So what we want to do is make this path high impedance. So the first patent to mention doing this was by Blumling back in 1936. He was a fantastic inventor. You can thank stereo phonographs to him, phonograph, right? Lots of interesting early radar stuff and that to him. Unfortunately, he died early in World War II in that they were testing an experimental radar, an airplane, one of the first radars in an airplane, and he was in the airplane and it crashed during the test and killed him. And it was not a good story. And since that death, they changed all sorts of rules about how the leading scientists could not go up in those experimental airplanes. But if you look at this page out of the patents and you compare it with what you see in like the AWL handbook and that, some of these baluns, quote unquote balun, chokes, are very similar to stuff we're still doing today. And I mean, he just was way ahead of his time. But the most common back in those days was called a sleeve or bazooka balun. And in fact, the word balun was invented, first used and applied to this, even though this is not appears to be balanced. So what is happening here is this is the outside of coax. These kind of dark lines, a quarter wavelength long, connected to them, going back up the quarter wavelength, is this outer shell around it. So what's a quarter wavelength look like to the signal? Very high impedance. It doesn't want to go down this path because it's high impedance. So where does the current go? It wants to go along here. So IC tends to be small. There's only one trouble with this device, is that it looks at one frequency, right? I said that this is a quarter wavelength long. So guess what? That's it. It only looks at that frequency. Well, that was okay for some things early on, but radars all of a sudden started having to jump frequency, and so this didn't work for them. Hams, we don't want to be at one frequency, doesn't work for us. So this has kind of disappeared, except in some testing in academia. But you will see these terms, sleeve and bazooka balun, all over the place if you go into look into anything about balance. Okay, so how do we make a wideband, quote, balun? So Rui chokes, right? Ferrite, bunch of wrapping of a coax, a bifilar. This guy down here, Jim Brown, K9YC, wonderful guy. If you ever meet him, he's just a great guy. Besides Roy's paper, anything but Jim on this subject you should read. The two of them put it all pretty well together, and I strongly suggest that you get a hold of those reports. Again, this is all online also. Just search for Jim Brown, K9YC, and you find a number of reports on these type of balance. I went out and visited him once, and it was interesting. He had one of these at the feed point of his antenna, halfway on the coax towards the shack, and another one right before it got into the shack. His is quiet. It's really nice. Okay. So what we want to do is know what the impedance is on that shield, right? So forget about the inner conductor, forget about the inside of shield. Just what is the impedance if you measure that? And over here, you can see that as we increase the number of turns, this is on log scale, the impedance in ohms greatly increases as the square of the number of turns. So what we want is high impedance, so the current on the outside shield doesn't want to take that path. And you can see that for some number 43, up in this frequency range, he's getting thousands of ohms of impedance. That's what you want. So here is a chart from G3TXQ, and I find this chart very valuable. So we got frequency across the bottom. Vertically, we have all sorts of different types of chokes, some with air, some with ferrite. So dark green is what you want, greater than 8,000 ohms, okay? And you'd also like the black line, which is the wheel, is greater than the reactance, the imaginary part, okay? Well, if you look down at air core, you never see the wheel greater than X. You see some green, but over very small areas, lots of red. Air core just doesn't cut it for us. You come up here to the ferrites, and like the previous ones you saw, okay, lots more green, okay, which is what you want. Lots of the time that the real resistance is greater than the X, which is what you want. This all looks good, okay? Now, you've all probably heard about the Walter Maxwell quote, balun choke, which just is a bunch of ferrite beads on it, on the coax. Does not do nearly as good as wrapping turns through a ferrite, because it only improves as linear. While these improve as square. The other thing is, notice that where I want stuff is a function of frequency. So usually what you see is some stuff in 31 mix and some stuff in 43 mix. Having one that covers the entire frequency band that we care about doesn't happen very well. Okay. So getting close to the end, can chokes blow up? Can the ferrites blow up? Yes, they can. You get enough stuff on that outside shield, and it can get in hundreds of watts, and they will blow up. I mean, I know people have been burned by touching them. So the energy has to go someplace, right? And so watch out for that. Make sure that they're rated for what mismatch you're going to have. And if you have an off-center fed dipole and you try to use it at all frequencies, you're probably going to get some pretty bad mismatch. Okay. Balance of the balanced current on symmetric job, right? The job is not to solve the VSWR problem. However, if they do get that balanced current there, it's taken care of. Remember that your rig can see 1-to-1, but that balun choke is still going to see that high visual. Be careful about that. And I recommend Dean's article, Don't Blow Up Your Balun. He made the mistake of thinking he was going to transmit on 10 meters, had the antenna set on, selected was the 10-meter beam, but his kilowatt amplifier and his rig was all on 40 meters. So guess what the visual was like? Not good. So high quality balance and chokes are useful. Use current balance or current chokes. Get high quality ones. That's a little bit of trouble, so ask people around, because few choke manufacturers actually supply measurement data, and you want ones with high R, not just with high X. Those are the references I have, which I said to, and I believe I'm out of time.
I think we have a few minutes for questions if anybody has any questions.
Just a quick one here, Leon.
Go ahead.
About the W2DU balun, you're absolutely correct that the impedance goes up only as the number of cores rather than the square of the number of turns. So it has much less impedance for a given volume. But the advantage of the W2DU balun is, first of all, it's convenient to make on large diameter coax. Like
I agree with that. I agree.
And the other one is that it will dissipate a lot of power. Those are the advantages, and of course, for the trade-off of lower impedance for the same size.
The other thing about that balun is that not all ferrites take the same load. The ferrite closest to the feed point takes more, and as each one goes on, takes less and less.
Walt told me that he observed that, and so I bought a bunch of baluns and I ran a whole bunch of tests, and I never was able to duplicate that. So I asked Walt about it, and he was never able to duplicate it either.
Oh, that's interesting.
I couldn't understand why that might happen, and so I wanted to observe it first, but I never was able to.
Ah, that's interesting. So when you did that, were all the ferrites touching each other, or were they spread apart?
They were touching each other.
Okay.
I can make a comment. Hi, Bill. Hello, everyone.
Oh.
Yeah, go ahead, Mike.
Go ahead.
Back some time ago, then he had WHAD was into amplifier design. And they brought a kilowatt amplifier to the FCC lab when I was there. We were looking into it. It was a tube type thing, of course. The final amplifier choke was, or coil, was on a G10 epoxy form. I said, why don't you use ferrites? And Denny was there along with his engineer. His engineer sort of became almost paralyzed. And Denny says, "Tell him, Bob." And Bob says, they detonate.
Very good. Any other questions?
George, I might want to add one to that. I read an article that was related to Roy's article about does the W2DO balun really balance the currents? So I set up an experiment for that, and I wouldn't have believed it. It is remarkable at balancing the currents into the two arms of the into balanced loads. I had them into resistors of unequal value drastically, and the currents it divides the current exactly as it's supposed to. I didn't believe it.
No, keep in mind that coils go into self-resonance with distributive capacity at some frequency, and that can either be good or bad.
And it seems, I would be interested in other people's opinion. Roy, you might have some thoughts on this, but that style of balun, WTDU, seems to me to be something that can handle highly reactive currents and still work as a balun to balance currents, whereas many of these others where you're passing through a core, that we think that might be a problem, but that's something we need to study more.
I don't think there's anything special about the W2DU balun versus one that's, say, multiple turns on a single core. Your objective is to get a high impedance, as Bill pointed out, and you can get that either way. Of course, you do need a lot more cores, as he also pointed out, in order to do it with the W2DU balun. But both of them can be very effective. But what you want to do is you want to have quite a high impedance relative to the impedance seen looking back down the outside of the coax. And in my experience, somewhere around 500 to 1,000 ohms is often adequate in practical applications. The nice thing about ferrites, as Bill pointed out, is the fact that they're really broadband, so they'll work over a very large range. But typically also your ferrites, the impedances tend to be resistive. They're not reactive. They're not inductances. They look like resistors. And therefore you do have the potential power dissipation problem, but it's a matter of impedance match. If you have a balun that has very low impedance, then you'll have fairly high current flowing through it. If you have one that's got a very high impedance, you have very little current flowing through it. So in both of those cases, your I squared R loss is very low. In one case, because your I is low, and the other because your Z is low. And so long as you maintain that, you won't typically have a power dissipation problem. When you have a power dissipation problem, it's when the Z is somewhere around the impedance of this path that goes down. And then you'll maximize the power transfer to the balun, just like any other power transfer problem. So that's the main objective in designing for a balun impedance. And how you get that impedance really doesn't matter. You can do it air core, wrap your turns around a bottle, wrap them in a loop, use ferrites, however you want to do it. Of course, some of them are more broadband than others, and there are other trade-offs, but any of those will be effective so long as your impedance is high enough.
So thank you very much, Bill. Excellent presentation. All righty, so bring the official part of the meeting to order.